Probably just going to be finding, well, pretty much what the title says, just finding and then maybe solving any questions I find related to oscillation in preparation for Friday's test. Okay, these don't work. So, 2000. Conducting an experiment, a simple pendulum. There. Okay. This is one. So let's write this down. This should be 2000. Okay. Okay, I mean, I might as well solve it. Let's have a look here. GU at an unknown location. Okay. Use a reasonable number of significant. Okay. Well, whatever. I'm probably not going to actually end up calculating that stuff because that's just like whatever. You just plug it into your calculator. However, let's have a look here. This looks pretty easy, but yeah. I don't know if it's worth bothering to graph it. I mean, I guess to graph it, I'd have to calculate t, which I'm not going to calculate. So I guess that's pretty much out of the question. Although let's assume that we have done it. Okay, so A is just plug-in stuff. Well, I guess I should probably, wait, what? Which records the time T10 for the pendulum to undergo 10 full oscillations. Oh, okay, so they already give you time. So this is just like 0.762 or whatever. This is like 0.5 something. Okay, so you just divide all these by 10 to get this, and then you square that for that. Okay, cool, sure. Then B, okay, let's assume that we have some line. Assuming that each pendulum undergoes small amplitude oscillations. Not sure what small amplitude oscillations means, but I'm going to assume that's just like, it'll fit the Taylor approximation. From your fit to determine the experimental value G experimental of the acceleration. Okay, sure. So what we know is that we'll have some slope here. So we don't know what the slope is. Let's just assume the slope looks something like that. Okay, now what we've graphed, the slope, m is equal to t squared. Well, let's just say that m is equal to the slope, t squared over L, times some constant a. Now, what we know from the period equation is that t is equal to 2 pi squared L over G for any simple pendulum. Now, if we just solve this out really fast, then we get that G is equal to 4 pi squared L over T squared. Okay. This is actually pretty funny. We had a physics lab on this. Like literally, it's literally a lab. So yeah. Anyway, we have this for G. Since our slope is T squared over L times A, the a is like whatever. But our slope, if we take 1 over the slope, okay, 1 over the slope, then we will get our g. At least presumably so. We'd get our g. Well, no. Sorry, not just 1 over the slope. 1 over the slope times 4 pi squared times 4 pi squared is our g. So assuming that we knew our slope, assuming that I did end up graphing it and I did actually calculate the slope by just doing rise over run, then I could take the reciprocal of the slope multiplied by 4 pi squared, and then I would get gexp. Okay, so now, or g experimental, rather. If the measurement apparatus allows a determination of GU that is accurate to within 4%, is your experimental value in agreement? Okay, so what we need to test, is we need to do error analysis. So assuming that I knew our quantity here, 4 pi squared over the slope. Let's just call this slope S, right? Okay. Assuming I knew this is the value of g experimental, then if I did minus g all over g, if to within 4%, if I did 100 times this, if this is less than 0.04, I think our value will satisfy. I think. Someone informs you that your experimental apparatus is in fact near the Earth's surface. Assuming that your experimental value gexp is exact, determine the magnitude and direction of the Earth's acceleration. Well, I guess from this, we now know that this is wrong. Like, it's not true. But anyway, assuming that our g experimental is exact. Okay, sure. Let's assume that our g experimental is exact. Then, with a constant acceleration a. Okay, so again, we have no idea what our 4 pi squared over the slope is. Although, we can kind of induct it. Okay, let me actually quickly calculate this. Just to get a quick estimate here of what we're looking at. So, let's just take the first 2 data points. So it's 889 squared. Okay, that'll be our t squared. And 0.762 whole squared. Thing. Okay, so that's our t squared. T squared is the y-axis, I think. Yeah. Okay. Over 0. I should have just divided it the other way in the calculator already, but whatever. That's bad calculation on my part. Okay, so now let's put parentheses around this whole thing. Do 1 over this times 4 pi squared. Let's check what our g value is. Wow, our g value is 11.296. It's not good. Okay. Well, in that case, it's pretty simple. So if our g value is 11.2969, or g experimental rather, then our A value must be this minus G. And it is pointing in the same direction as G, which I guess we can assume is downward. So minus 9.8. That is our G experimental. At least I think so. This is kind of a strange question. But let's see here. Okay, sure. Yep. G experimental. Okay, this is what I did. Wait. This is exactly what I did. Why did I get a different slope? I mean, why did I get a different G? That's weird. Okay, well this is what I did for error analysis. I don't know why I got a different numerical value for G. Maybe I subtracted the wrong way or something, but this is exactly the formula that I wrote. So unless I like calculated the slope wrong, which would be extremely troll. Yeah, I did this minus this over this minus this. What? That's so weird. Okay, I don't know. Whatever. But yeah, this is pretty much exactly what I did. And yeah, this is exactly what I did. Okay, cool. So yeah, I don't know why my numerical value was different, but my process was exactly the same. So I don't know. I don't know what happened there. But yeah, that was that problem. Okay. So let's check 2001 now. Okay, this is some force analysis. Momentum, mass, energy. Okay, I haven't learned gravitation yet. And this is torque. Okay, I've done that problem before. Nothing in 2001. Oscillation is kind of uncommon in general. Like I don't see too many oscillation problems. Quite elastically, speed V, position, impulse. Oh, spring, incline. Nothing? Come on. Okay. Then potential energy curve. That's ridiculous though. They had a spring, I mean it had all of the parts to make a great oscillation question, and they didn't do it. Hi Flora. Network, speed, kinetic energy, force, power. Okay, this problem is really easy though. Okay, I mean, I already did this problem in class today, so whatever. Yeah. I guess I'll write it down though. Just keep track of that. So what year is this? 2003 problem 2. Okay. And what is this? Counterweight. Okay, this is just conservation of energy, I think. But let's see. Okay, no oscillation. I don't know why I even suspected that could be an oscillation question, to be fair. Pretty ridiculous of me. Okay, I've already seen this one. It's not. Finish. Oscillation. There we go. We're in business. Okay. And a nice review of like some rotational inertia stuff. Okay, let's do this problem. I also write it down quickly. So it's going to be 2004 APBC problem. Okay. Let's have a look here. So the pivot is located. Okay, rotational inertia of the rod. So do they not give you? I mean, like, I know what it is. I'm just surprised that they didn't give that to you. Maybe they expect you to, like, derive that or something. Whatever. So it's just going to be the rotational inertia. So the normal rotational inertia is 1/12 ml squared, which you can prove through calculus, which I actually did in my, like, last time I recorded myself doing physics problems. I derived this. Then use parallel axis plus. Maybe I'll actually try doing this without using parallel axis and knowing that. Unfortunately, I'm not doing that now though, so plus ml squared over 36. This is 3 ml squared over 36. So this is 1/9. 1/9 ml squared. The linear speed of the bottom end of the rod when the rod passes through the vertical. Okay. There's probably two schools of thought here. One of them would be to just use rotational conservation of energy. Or you can do linear conservation of energy and skip some algebra. Although I'm kind of scared that just won't work. So I'm just going to do rotational and be not adventurous here. Okay, so we know, of course, that M, then if you think about like where the horizontal position would be, it'd be like here. Like this point has moved from here to there. This is a distance of 2L over 3. So the original is mg, or like the gravitational potential energy is 2L over 3. This is going to be equal to 1/2 I W squared. Okay. Now, W. Yeah, okay. So there's not much black magic happening here. It's just going to be equal to 1/18 mv squared. And that is why. This right here is why you don't use linear conservation energy. Don't. Yeah. Okay. So now, what are we allowed to use? Okay, we're allowed to use MLG. Okay, great. So the M's cancel out. We don't care about that. Now, if I multiply everything by 18, I get 12 GL is equal to V squared, I think. So V is equal to square root 12 GL, but that's actually 2 square root 3 GL. I'm actually going to check my work on that because I find it very likely I fucked up some algebra somewhere. Haha, they did expect you to do the integral. That's funny. We still got it though. Yep. This is precisely what I did. GL over 6. Hey, look at that. Copped a cool 7 points. No. How many points? We've already gotten 10 out of 15 points. We haven't even done the third part yet. Okay. Wait, what? The rod is brought to rest in the vertical position shown above and hangs freely. it is then displaced slightly from this position. Calculate the period of oscillation. Okay, I assume that they just say it's displaced slightly to get you to remember that small angle approximation only works for small angles. Okay, so we know that this acts as a physical pendulum. This is not going to be a simple pendulum. Although, you can actually solve a physical pendulum as a simple pendulum if you do some black magic. However, we're not that smart, so instead we're just going to do the thing. I over mg 2l over 3. I is, of course, mgl over 9 equals square root mgl over 9 all over mg 2mgl over 3. Now we're going to do some cool fraction simplification here. I think this is just square root 2/3. That's definitely wrong. That's, or maybe it's square root 1/6. Okay, actually, I don't trust myself. So here, okay, we're just gonna make a big square root here. mgl over 9 times 3 over 2mg. Okay, so it is 1/6. Square 1/6. Okay. Now we can just check that real quick. That's not an answer key. C continued. Oh, stuff definitely canceled that wasn't supposed to. The pivot. Oh, it's the pivot to the center of mass? Oh, yeah, also, yeah, the G and the L won't cancel. I don't know what I was doing. That was troll. This was off, though. I didn't realize it was L over 6. I thought it was... Oh, it's the pivot to the center of mass. I made the same mistake on a homework problem. Okay. That's good. That's good information to remember, though, that it's pivot to center of mass and not just pivot to the end for a physical pendulum. That's good stuff to remember. Okay, cool. Yeah, sure. I don't know what happened there, though. That I substituted I wrong. Anyway, okay, sure. That's 2004. But yeah, I mean, I basically did that. Okay, let's see, 2005. The goat air resistance. Okay. This decreases, by the way. Decreases to 0. So just terminal velocity. Wait, actually, magnitude of acceleration. G points down, huh? And then, interesting. As the ball moves upward. I think this might increase, actually. Not sure. Probably have to think about that properly. Okay, orbital data, that's not it. Oh. Angular momentum, speed V, elastic, and there's no oscillation. Cool. This looks like a fun problem to do. I might do this later. Just save that for myself. 2006. Okay. Oh, nonlinear spring. Yes, sir. Yes, sir. Oh, you know it. What? No. No way. How could they throw such a good problem for oscillation and not make it oscillation? I'm so disappointed in College Board. Okay, that's like incredibly free. Okay, some shit gravitation question. Oh, extension. Okay, this is looking good. V squared x squared. Best fit line. Wait, what? Huh? No. Come back. Okay. It's maximum speed, and the string becomes slack. No. What? Is there seriously no oscillation for this? Go data. Oh, wow, College Board. Selling on an astronomical level right now. Air resistance? Okay. Oh, wait, no. That's definitely not. Oh. Spring constant? I see it. I like it. What the fuck? No oscillation. GG, bro. GG. There's so many spring problems, and none of them are, like, come on. Small angle approximation. Okay. What? Okay. Well, rip. 2010. Come on, oscillation. More drag. How am I seeing so much drag force and I'm not seeing fucking oscillation? Okay, this isn't already know. Oh! Sine pi t over t? Oh, this is looking good, man. I see trick. Wait. Okay, velocity. No. Come on. Of the four. Impulse. Dude, what the fuck? Okay. Nice. They even had the trig function and they didn't make it an awesome. I'm so mad. Okay. Impulse. Oh, no, I've done this problem before. That's something. I've done this one also. Torsion. Whoa, we did this problem in class and it's incredibly free. Okay, that problem is like not even worth spending time on. Solve that in like 2 minutes. There we go. We're in business. Look at that. Oh, this is an insane oscillation problem. Hello? Dude, what? Good stuff. Okay. This is good. This is actually really good. Finally. Okay, let's do it. So Let's just... Okay, determine the equation for v of t. What do they give us? Oh, this is v of t. What? That's so stupid. Okay. Given that the equilibrium... Please tell me there's more. Okay, good. Swear, bro, if they sold me with a 3-part question after not seeing a single fucking oscillation for like 10 years, I would kill myself. Okay, let's see. Oh. Okay, let's see. So, determine the equation for v of t. So luckily there doesn't seem to be a phase shift. Given that, okay, whatever, that's fine. Equilibrium, whatever. Okay, so the amplitude is what? 0.1, 2, 3, 4. What the? Okay, so it's a 0.12, 14, 16, 18, 12. Okay. So this is, well, presumed there. 1, 2, 3. So 1, 2, 1, 4, 1, 6. Okay, so it's minus 0.16. Then the period is from here to there. Why the fuck are the units so shit? Oh my god. Okay, 0.6, 0.7, 0.8, 0.9. Okay, so this is... Okay, so the period is 0.8 seconds, which means that our omega value, which is 2 pi over t, is 2 pi over 0.8. So that's 2 pi divided by 4 over 5, which is going to be 10 pi over 4, 5 pi over 2. Okay. 5 pi over 2 times t. Now our phase shift is 0. Oh, and there should be a sine. Sine 5 pi over 2t. And it's minus, which is good. Okay. Given that the equilibrium position is at x equals 0, determine the equation for x of t, including numerical values for all constants. Okay, let's do it. So, actually, do we care much? Oh, no, actually, no, we do care much. So, here. What we know... So we could just directly integrate this, or if we were being a bit smart about it. Oh, wait, the equilibrium position is at x equals 0? Oh, that means that there is a phase shift for x that somehow went... Oh, wait, what? Hold on. I need to check something. We're gonna graph that on Desmos real fast. I want to make sure that I'm not like trolling. Minus 0.16 times sine 5 pi over 2x. Okay. So this looks about right to me. Yeah. Yeah. Okay, so my equation was correct. Then how can there be a phase? I don't know. Is there not a phase shift? Am I just trolling? At t equals 0. That's so weird. Okay. Well, I have less than half a clue why that's true. But I think we can presume, what we can presume is that x of t, it's like the integral of this, ish. So it's going to be x of t equals, also, do we have a mass? Okay, no, we do. So c is just w is equal to square root k over m, k is equal to w W squared. MW. Okay, that's that. That's part C, but here. So if we want to integrate this, we'll have to do U sub basically. So integral 0.16 sine 5 pi over 2t dt. Okay. So the integral of minus sine x should be cos x. Then I think we need to divide by 5 pi over 2. So I mean, actually, we can just like construct what it will be. So I don't know why I'm even bother integrating it anything. Okay, we'll just round that to 0.02, I guess. Okay, so it'll be 0.02 cos 5 pi over 2 t. This is 1, so then minus 0.02. I guess. I mean, I don't know. This is really strange. Really strange. What's going on here? I want to check this. Unless I'm like not thinking about this right or something. Is this the right question? Oh yeah. Uh-huh. Yeah. Okay. Yeah, sure. Is 0.7 on the graph? What? Hold on. Oh yeah, that is 0.7. I can't fucking count. Okay, that's my bad. Whatever. Okay, this is what we did. Yeah, so phase shift is 0. That's what I did. Okay, this is what I thought. But then the equilibrium. Okay, maybe that equilibrium position was just there to throw me off. Like, I don't know what. Okay, so I would have lost 1 point. That's pretty sad, actually. This is a stupid way to do it. Yeah, you should. Yeah. Okay. Let's not look at the rest of it. I'm gonna solve it. I don't know what that equilibrium position thing meant. What does that mean? X equals 0. Like, given that the equilibrium position is at x equals... Was that just there to throw me off? Like, what's going on? If I plug in t equals 0... I don't know. It's weird. I didn't think about that later. I am thoroughly confused about that, though. Okay. Okay. Rough surface, huh? Okay, so towards the equilibrium position. Friction goes this way. What also goes this way is K d over 2. And then here, this is still kd over 2. But then friction goes the other way. Okay. Draw a sketch of V over T. Okay, actually what we're gonna do is we're gonna be a bit more rigorous here. We're gonna actually solve. Wait, V over, in what case? Wait, what? Wait. Is this V over T? Oh, is this from, what? Hold on. Oh, I see. Okay. So this is what's going on when it releases from rest. Okay, so normally the velocity would be like a sine function of sorts, but this is like not quite a sine function. um I really don't know. Like, okay, we can assume at a negligible change in the period. What was the period? The period was 5 pi over 2. No. It wasn't 5 pi over 2. It was 0.7. Okay. Interesting. Okay, well, the initial velocity we know is 0. And then we know that the velocity will go up, hit the period point, then go down back to 0. Then it'll go back. Okay, so if we assume that this is the period, it'll look something like this. I think. Now, what worries me about this is that we're not given a negative y-axis. So, yeah, okay. Oh, right, yeah, I forgot about the damping. Oh wait, no, never mind. We are given it. Okay. Yeah. That's pretty much what I expected. Okay, yeah. So I would have gotten 2 out of 3 for this. I switched the diagram in my own thing, but this is what this is the point. Yeah, I switched the diagram, but this is what I meant. So I would have gotten, okay, yeah. Oh, I forgot about normal. Okay, whatever. That's like that doesn't matter. Normal force and gravity is like meh. Oh wait, hold on. Oh no. You would need to. Okay, whatever. I would have remembered that on the actual. I was doing it properly, probably. 4, 2. I forgot about the damping, even though I literally said like out loud, like remember the damping. Dude, I would have lost 2 points on this FRQ. That's like terrible. Okay, whatever. Fine. 13 out of 15. Rip. Yo, another one? Oh wait, I didn't even check the rest of this one. Hold on. Conservation of mechanical energy. Okay. Presumably, okay, there's nothing there. Nothing there for us. Us poor fools. So what is this? What's going on here? Okay. Time, velocity. Oh, that looks so much like not oscillation, actually. Uh, oh, shit. Okay, we have like the bare minimum of what qualifies for an oscillation question going on here. Like the bare bones of what qualifies for an oscillation. But, okay, sorry, yeah. I mean, I guess I'll do it. Like, I guess. Okay. Actually, I take a picture of this. Okay, let's take a picture of the diagram, and then I'll take a picture of all of the pages individually. I still can't believe I forgot about damping on that question. That's literally so stupid. I said it out loud. I remember damping, and I forgot before I checked the answer. Truly the lowest of the low. Okay. This is weird. Okay, well, let's actually like read the problem. I guess more relevant information for the problem. So I bet you that you probably don't even need to look at the diagram because all the information will be in this picture. But let's see. Okay. Oh yeah, should they tell us what X is? Okay, I'm gonna V over T. Cool. Okay. This looks pretty free to graph, so I might actually do the graphing this time, just so that I have some level of relevant information to solve the rest of the problem. Okay. Let's have a look here. So from, I mean, like pretty much from here-ish, it's all about the same. I have no idea what to set the axis to. So I'm just going to set this. This is going to be 0.25. It's going to be 0.5. Cool stuff. Okay, we're just going to bam, bam, bam. Set that like that. 0.75. Where is 0.75? That'd be like right here-ish. I mean 0.48, that's like basically the same thing. Come on. And it's gonna be like there-ish, thereabouts. 0.43. Be like here-ish, whatever. 0.25. Oh, we hit a huge drop off there. Wait, this is 1. Oh, okay, yeah. So then 0.25 is like here. Okay, so what does it ask us to do? Okay, so it's not supposed to be linear. I didn't fuck that up. So it looks like that. What? What did it ask us to do for part B? Solve for x of t. Oh, graph x of t. Yeah. I didn't get the rest of it. Yeah. Okay. Okay. Sketch x is a function of time. Okay. Well, what we know is that x is the integral of v. And what we can kind of say is that from x is equal to 0.79 onwards, our slope is like 1/2. So from like here, let's just say, okay, like from here-ish, hereabouts, it's just going to be a straight line like that. Now, for this here thing, I mean, what is the velocity going to be? The velocity should be like, okay, well, acceleration is kx over m, right? The only thing that acts on this is the spring force. So the acceleration is kx over m. Then the velocity is going to be what, like kx squared over 2m. Then here we're going to have kx, it's going to be like a cubic looking thing. What the fuck does a cubic look like? Like, I don't know. Like, maybe it looks like this. Or maybe it... I don't know. Let's guess it looks like that. Whatever. If I lose a point there, I lose a point there. I want to know how you're analytically supposed to do that, though. Yeah, sure. The slope... Okay, yeah. So, yeah, there you go. Come on. Yeah, look at that. It's concave up. Yeah, okay, yeah. See, we got it. I'm cracking. There. calculate the time at which... Calculate? What? Okay. Sure. I find that mildly difficult to do, though. Actually, not particularly. So here's what we know. What we know is that at t equals 0.79, the glider is at the unstretched position, i.e. at 0.25 meters. That's what we do know. That's when it'll lose contact with the spring. No, wait, actually? No. Hold up. I think that's some cap if I've ever seen it. I stretch it back. It's gonna go forward an extra 0.25 meters. So the equilibrium length was where? Okay, so it compresses back 0.25. Normally it's where? Okay, so it touches an uncompressed ideal spring. Okay. So the uncompressed ideal spring gets stretched back 0.25 meters. Then at t equals 0.79, I mean, it shouldn't return to equilibrium length, should it? It should go like x forward from equilibrium length, if I had to guess. Or I'm completely off base. This is actually a hard question. I have to think about what would it only go to equilibrium length? Or I don't know. I'm having an extremely hard time thinking about this. Okay, even though I think it's wrong, I'm going to presume that at t equals 0.79, the glider is at 0.25 meters. So I cannot for the life of me think where else it would be. Like if I look at my own graph, I mean my own graph is completely imprecise, so I would never know. But I guess it's at x equals 0.25. Oh, then it's very free because we know that this thing just travels like half a meter every second. So, I mean, then you just do 1.75 divided by 2, and then whatever. So I want to see, how did they do it? Okay. What? You have to use the graph? Huh? You fucking kidding me? What is this? Dude, this has to be a joke. Like, this has to be a joke. There's no way. There's absolutely no way that's what they wanted you to do. What? 2.9 crap? What? What the fuck? Okay, that was... Yeah, I don't know, man. I genuinely do not know. That's like absurd to me. How could they possibly expect us to figure that out? Yeah, I mean, no, this absolutely not. Would have lost a point there for sure, 100%. Yeah, okay, and this stuff is just trivial. Like, who cares? Yeah, whatever. Okay. But how did they expect you to... What? Okay, what's the alternate solution? Do they have an alternate solution? Oh, dude. Oh, never mind. Okay, this is exactly what I did. Oh, wow. Okay. Never mind. Okay, no. This problem is completely, like, okay then. Yeah, sure. Okay. Okay. You know what? This is a much more reasonable expectation of what they want you to do. And somehow it's like the same thing. What I want to know is why this alternate solution is not the main solution, and why instead they do this shit. Okay, whatever. I mean, fine. But anyway, we're actually good on points then. So then, okay. Determine the force constant of the spring. Okay, this is conservation of energy for sure. So 1/2 kx squared is going to be equal to 1/2 mv squared. We know v, we solve for k. Whatever. Okay. Determine the amplitude of the resulting periodic motion. This seems extremely free, no? Like, what's going on here? Okay. Amplitude of the resulting periodic motion. I mean, it doesn't seem bad, probably. So, wait, amplitude? Don't we already know amplitude? Like, wait, what? Hold on. Can it go further than that? Can't, right? I mean, this is just... One half k x squared. Yeah, wait, isn't this just 0.25? Or am I... I mean, the most it can go the other way is just 0.25, so that has to be it. Otherwise, I mean, Hello? Oh wait, no, this is not the right... Oh my god, I got scared out of my fucking mind right there. Okay, yeah, whatever, that's... Yeah, okay, it's just 0.25. That's stupid. The period of oscillation... T equals 2 pi squared m over k. We're given k, or given m, we solved k. 2 pi is 2 pi. Okay, that's that. This is a good problem, though, I have to say. I'm still... I'm in awe that this is the main solution still. I cannot believe that they would pick this shit solution over this. What are they doing, dude? What are they doing? This is so obvious. And they picked this. 2.9 large... Okay, whatever. College board never fails to astound me. That's all I'm saying. Anyway, so far scoring very well on... Oh? Non-linear restoring force? Huh? 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 Yeah? Yeah, you know it. You know it. Speed of the cart, impulse. Okay, good stuff. No oscillation. That's definitely not oscillation. That's kinematics. Okay. 2015. We're now basically in the modern era. I've done this from before. That's not it. Oh, data. Oscillation. Bam. Well, I mean, yeah, this is oscillation, I guess, but this is like not even worth doing. It's just 2 pi L over G. Yeah, come on. This is really not worth doing. I'm not. Yeah, I'm not hearing it. Oh, actually, hold on. The one thing to be careful here though is that it'll be 2 pi L over G all over 2. It's not the period, it's half the period. So yeah. Not quite what I'm looking at here. Velocity, straight line. G. Wait. Oh. Huh. This part in... Okay, like the smart way is definitely not doing it with oscillation. Although what you could do is you could treat this as a simple pendulum. I mean, not a physical pendulum. And you could do T is equal to the square root of I over mgh. And then you could solve for G. That's what you could do. Now, if you do that, you're totally, like, stupid. Like, I'm not fucking around. Like, that's, like, if you do that, you're beyond help. But, I mean, it's definitely possible. I want to see what I do want to see, though, is I want to see if they put that as an alternate solution for problem 3, like, before I move on. Wait, what? Yeah, okay. So I said this. I mentioned this correctly. You do have to divide by 2. Very key thing to remember. Okay, yeah, that's whatever. You do this. Wait, okay. So did they put it? Did they put it? No, I don't think they did. Sad. Wait, oh, alternate? Oh, no. Linear. Okay. No, never mind. Yeah, but you can do that using the equation for a physical pendulum. It's period. Definitely. Actually, I guess you don't know. You don't have T, so no, I guess you couldn't do that. Never mind. Acceleration. Force Cool. Non-linear. There's no way this is oscillation. Evidently, it seems I was wrong. Okay, let's do it. So, I'm kind of gonna, well, I mean, should I do the rest? Okay, the first part's just like content. Okay, I'm gonna like speed run the rest of it. We're not gonna like actually do it. Okay. Whatever, I don't care about this. Speed of the blocks, inelastic collision, kinetic energy. You just do it. Not not that deep. Yeah. You take the velocity from this, then you do 1/2 m plus m bf squared. Maximum distance d, you do conservation of energy, whatever. Net force, don't care. Don't care. Okay. Now, do the two blocks, which remain stuck together and attached to the spring, exhibit simple harmonic motion after the collision. What would have to be true for them to exhibit simple harmonic motion? That's probably a good place to start. Well, one of the defining characteristics of simple harmonic motion is that... So, okay, what could be used? It could be the period or like omega. Wait, well, no. Because for simple harmonic motion, I'm pretty sure the restoring force has to be minus kx, right? Otherwise, it's like oscillating motion, but it's not simple harmonic motion. I think. I'm gonna check the answer for that. I'm actually genuinely curious what the answer to this is. I'm gonna write this down though. 2016. I don't even know what would have to be true for that. Interesting to think about though, definitely. So let's have a look. Scoring guideline. So let's see. What's the just? Okay, it's. Huh? Oh, okay. So it's F. Okay, it is no, right? Yeah, so it's not a linear force. Okay, yeah. Look at that. Look at that. Look at that. We're in there. We're winning. We got it. We got it. Okay. I'm pretty happy with that. 2017. Let us have a look. Atwood machine? Yeah, that's definitely not it. Dude, what is going on with the amount of questions that want us to solve for G? Like, hasn't G already been done so many times? Who fucking cares, dude? Oh, spring. Oh, this has to be. MHK, okay. Conservation of energy. Is there any friction? Friction. Negligible friction. Good stuff. Okay. Okay, whatever, you just find that. This is just going to be conservation of energy again, determination. Expression for the time when the block collides with the spring. Whoa. Oh. You know what I bet it is? You probably still have a differential for T. That's what I guarantee it is. I bet good money. I still have a differential for T. Wait. Yeah. If you don't solve a differential for T, like, how would you even do that? Oh, wait. Oh, no. It's not constant acceleration. Yeah, I mean, you can't use kinematics. What else even has time in it? You'd have to use calculus, right? I'm gonna check the answer for that after. Let's see. Yeah, okay, whatever. Who cares? Okay, dude, they're literally talking about differential equations here. There's absolutely no. Okay, first of all, I'm sad that's not an oscillation problem. But second of all, there's no way that this is not a differential. 100%. You solve the you create an expression for acceleration, you differentiate or you integrate it twice to get position, and then instead of solving for x, you solve for t. So you manipulate it such that you get t is equal to something something. And if it's not that, then I'm interested to know how you would do it. Yeah, okay, whatever. Simple harmonic motion? Wow. Okay, that is something I did not expect. I will say, that is something I did not expect. T is 1/4. Why is it 1/4? Not 1/2? I don't get it. What? Why is it not 1/2 T? Hmm? Hmm? Okay, no idea. I want to see if my way would work, though. Let's find out. See, but the thing is, I wouldn't actually get the first point. Because I wouldn't have done it with simple harmonic motion. That's so stupid. But, I mean, okay. Let's see. The acceleration minus kx over m. Okay, this is our acceleration. Okay. Yeah, that is definitely our acceleration. Okay, so minus kx over m. Integrate this. Minus k over m. I don't know. I think you need to do some chain rule nonsense here, but beats me. Okay, no, it definitely doesn't work. Interesting. Okay. You know what? I'll concede problem part C. Would not have thought to use simple harmonic motion there. Well, I guess actually, since that was a simple harmonic motion problem, I should probably write that down, huh? 2017. What problem was that? Part 2. EPPCP2. That's genuinely pretty insane, though, I have to say. Definitely would not have thought of that in test. Okay, let's see, 2018. So it's kind of interesting how oscillation has gotten more popular over the years. That's an FRQ question. Electromagnet? What the fuck? Okay. Does not look like. Oh. No. Sad. Okay, 2019, set 1. Let's go. Wait. What? Oh, no. No, I've done this one before. Okay, set 2. No. Definitely not. Oh, toy rocket. Doubt it. No. Okay, well, I guess that's all of them. Surprisingly few oscillation questions, I have to say. Physics 1 probably has more. But yeah. You saw on the stream then.